Okay, everyone, let's take a look at numbers 8 and 9 in section 6.3. They're very similar. We're going to find the volume of the solid obtained by rotating region A in the figure below. So I reproduced the diagram, and it's kind of a generic diagram. Um, you've got a parabola, which is x squared plus y equals x squared plus b, and b is different values. And again, your problem might be slightly different. In my number 8, b was 8, and my number 9, b was 3. So those numbers will vary. Basically, that just shifts the parabola up or down along the y-axis. Okay. So there's that. And then A also here, which is an X value here that denotes the boundary really of region A. It varies as well. In my number 8, it's 6, and over here it's 9. So, you know, your numbers again could be slightly different, as well as the axis we're rotating about. I must be missing some language here, but it should be obtained by rotating it about, yeah, about y equal 8, I'm sorry, or y equal -9. So these are horizontal lines. And again, these numbers, you might have y equal 4 or y equal 5 or something different. Um, the region is A, I've shaded in. There was also a region B underneath here, but both of these problems, I think, have region A. So let's just take a look at number 8. So first of all, we're going to rotate region A about y equal 8. And in this case, B is 8, little b is 8, and little a is 6. So I went ahead and just replaced B with 8. I got y equals x squared plus 8. So there's that curve. And then x equal 6. So A is the value of 6. So when x is 6, the height, what's this height right up here, is going to be 6 squared plus 8 in that case, or 44. So I just redrew the picture here. We're going from 8 to 44 here, from 0 to 6 here, and there's the shaded in region. And of course, y equal 8 would be this horizontal line. And we're going to rotate this region about this axis. I'm not going to try and draw that three-dimensional shape, but on the outside, it will look like a cylinder. If we're looking this way, we'll see a funnel-like interior of that solid. And we're interested in the volume, right? What's the amount of material need to create, if you will, this solid, three-dimensional solid. Okay, so the way we do this then is we're going to take look at integrating from x equals 0 to 6 at an arbitrary distance x here. I will create this rectangle to represent this area of the region A, and then rotate that about this line y equals 8. So it's going to come out of the page and go back into it down here. And hopefully you'll see what we'll have is a washer, right? So it'll go back into the page right about here, and we will have a cross section is a washer, right? So there's that cross section that we're looking at, and I've recopied it down here. Axis of rotation again is y equal 8. We have, I call it the little r is the radius of the hole, the inner circle, and then the big R is the radius of the outer circle. And basically, the cross section area then is just going to be what? Pi big R squared, the area of the big circle, take away pi little r squared, right? And that's the washer method, basically. So what is little r? Of course, little r will be from the axis of rotation to the bottom of our rectangle. So what's the value of r? What's that y length? Well, it's on this curve here. So the y value of the top is, again, x squared plus 8, right, for an arbitrary value of x, And then the bottom is always on y equal 8, right? So from here to here, this little segment right there, the y value of that is the value of little r, right? And notice little r varies from 0 basically all the way up to what? From 8 to 44, which is what, 36, I think, right? And so uh, x squared plus 8 again is the top, 8 is the bottom, subtract, and I just get x squared. In fact, that's the radius, and you can see that by the time we get to 6, right, x squared would be 36, and that indeed is the distance between 44 and 8. That's the radius of this hole in that case. It's varying from 0 to 36. And then what about big R? What's from the axis of rotation to the top of the rectangle? The top of the rectangle is always on y equal 44. So basically it's the difference between 44 and 8 or 36, right? The big radius R is always 36. Okay, so with all of that, we can now integrate, right, the cross-sectional area, which is just pi big R, so 36 squared minus pi little r, x squared squared. I'll factor out the pi, and in that case, r, which is 36 squared, is 1,296. X squared squared is x to the fourth. So here's my integral. Now I can find the antiderivative with that. Evaluated at the upper limit of 6. Of course, at the lower limit of 0, it turns out to be equal to 0. And then I can convert that to a fraction. They do want the exact value. So you have to do a little bit of work on that to get that to work out. There is the result for the volume. Okay. Let's look at the other one, number 9, right? This one was rotating at about y equal -9. In this case, b was 3 and a was 9, so it's going to be y equals x squared plus 3, and this value of x here, the a, will be 9. So I redrew that picture again down here. So here's the curve now, y equals x squared plus 3. When x is 9, the height of the function is 84, which I messed up when I first did it. So 84. And then notice this time, we're integrating with respect to x from x equals 0 to x equals 9, but we're rotating this time about the line y equal -9 way down here. Okay, so that means this thing is going to come out and go back into the page. It's going to be way down here somewhere, right? And we're going to get, again, that washer, right? Much wider washer, okay? The axis of rotation again is y equal -9, and the inner radius, my little r, is going to be from our axis of rotation, y equal -9, to the bottom of the rectangle. So from here to here, that distance right there, that's the little r. And notice the top is on this curve, which is y equals x squared plus 3. The bottom is the line y equal -9, so x squared plus 3 minus a -9 gives us x squared plus 12. That's the distance between the two. Or you want to just think about it, the distance from the x-axis, which of course is y equals 0, to y equal -9, that's 9 units, right? And then the distance between the x-axis and our curve is, of course, x squared plus 3. So x squared plus 3 plus 9 gives me x squared plus 12. Okay. And then what's the big R? Big R will be from this axis of rotation all the way to the top of the rectangle. Well, that's from 84, y equal 84, down to y equal -9. So 84 minus -9 is positive 93. So again, we've got the same setup. We've got pi. This time we're integrating from 0 to 9. Big R squared minus little r squared. So big R squared here is 93 squared minus little r squared, x squared plus 12 squared. So doing a little work, square 93. I messed up the first time, apparently. 8,649 minus, and then be careful, when I square this out, I get the first is x to the fourth, x squared times x squared. The inner and outer are both 12x squared, so a total of 24x squared. And last gives me 144. If I FOIL that out. And then being careful here, 8649 minus 144 is 8505 minus x to the fourth minus 24x squared. Okay, now find the antiderivative of that. 8505, x is the antiderivative of 8505, antiderivative x to the fourth. Antiderivative of 24x squared is 8x cubed. And then I plug in 9 and plug in 0 and subtract. Of course, at 0, it's equal to 0. Big old lovely looking fraction here. I get 294,516 fifths times, of course, pi. Don't forget that pi is out there. Okay, so some big old fractions we're getting here, but this is the way to proceed with these problems. Again, using essentially both cases the washer method. All right, hope this is helpful.